In section 7.7, we introduced the idea of energy diagrams and the stability of equilibrium. Our objectives here are to define and interpret energy diagrams and understand the concept of stable, unstable, and neutral equilibrium. We also want to be able to recognize these states on a graph. The motion of a system can often be qualitatively understood by analyzing the graph of the system's potential energy curve. This is an energy diagram. An energy diagram shows the potential energy of a system as a function of position. So one of the members of the system is moving in some way, and if you look at the position of that member, the separation distance between members, we can now create a graph of the potential energy based on where these objects are located. So let's look at a potential energy function for a block that's located on a spring. Remember, we said that for springs, the force is equal to a negative kx. We also said that force is equal to a negative derivative of the potential energy with respect to position. So as we look at a graph, we understand that slope or derivatives are going to be related to that slope. So when we look at x equals 0, we see that the force is equal to 0, and the slope should therefore also be equal to 0. We see that here on our graph, that at 0, we're hitting that 0 potential energy and have a 0 slope. Now, if we exert an external force on this spring, and we pull on this spring and we stretch it this way, we see that we now have a positive x value, which gives us a negative overall force. A negative overall force, when we look at the negative derivative of that, is now going to result in a positive slope. So when we look in the positive region of x on this graph, we see that we do in fact have a positive slope occurring in this side of the graph. If the force were instead to compress this spring and push it in, we're now looking at negative x values for the position of that slope. A negative x would result now in an overall positive force, and a positive force would correspond now to a negative derivative when we look at that, which means that our slope in the negative region of the graph should be a negative slope, which we do in fact seeing occurring here. We know that the potential energy function for a spring is equal to a 1/2 kx squared, which really gives us this parabolic shape that we've been looking at on this graph, which does in fact have the slopes that we are expecting it to have. This type of graph that looks like this, or really any graph that has this relative minimum on it, is corresponding to what we'd call a stable equilibrium. The x equals 0 position here would be considered an equilibrium position, and any movement away from this position would result in a force directed back to that exact same position. Basically, the object wants to continue to move back to that equilibrium. It's a restoring force. So in general, positions of stable equilibrium will correspond to those values of x where on that equation or graph for potential energy with respect to position, you have a relative minimum on that graph or on that energy diagram. Let's look at another potential energy curve. We can see that this curve is sort of inverted, going the other way. We do still have a point where x is equal to 0, which results in a force of 0 and a slope of 0. So the particle would be in an equilibrium if it was in that particular position. But this position is an example of unstable equilibrium. Here's where we have a particle that if it's displaced to the left or the right, it will actually accelerate away from this position. We see that in this spot here, as x is greater than 0, we have a force that is positive and a slope now that is negative. And the object is not going to be in that restoring force of trying to come back to the equilibrium, but instead its potential energy is becoming less and less as it moves away, so it is not going to try to restore back to that initial position. This would be an example of like a ball maybe sitting on top of an inverted spherical bowl. As the ball is displaced to the right in this diagram, we see that it will just continue to accelerate away from the equilibrium position. For these unstable equilibrium positions, they will correspond to values of x where your potential energy function has a relative maximum value on the energy diagram. Some situations have a potential energy that is constant over some region, and if we were to graph out this potential energy, we'd find that the graph for some of these objects is actually just maybe a constant. And so if we look at the overall derivative, it's always going to be a zero. This is what we would consider to be a neutral equilibrium. Small displacements to the right or to the left of this type of graph is not going to cause a restoring force, and it's also not going to cause a disrupting force trying to move it away from that position. This would be like a ball that's lying on a flat surface. So as you displace it to the right or the left, it's not going to accelerate either towards or away from equilibrium.